Anybody falls off the stage.
Our second speaker will be Chris Pattison, who will tell us about quantum fault tolerance with constant space and logarithmic time overheads.
All right. Thank you, everybody, for sticking around till the end of the conference and joining me on this Friday. So this is joint work with Quynh and Nguyen, who is in the audience here. And you can find our paper on the archive. So in general, this is a very involved construction, but I'll try to give as much flavors of kind of the high-level interesting points as we go along. So first off, why do we care about asymptotic results? Well, in general, I'm interested in what a fault-tolerant quantum computer might look like in the very, very far future, and sort of asymptotic results provide kind of a bit of a guide to that. The other thing is that we can oftentimes take these asymptotic results and maybe put them into practice and learn something about how to build more efficient devices, even in the non-asymptotic regime. There's also another interesting point, which is this says something about fundamental limits. You know, what is fundamentally the overhead of quantum fault tolerance? And then in some cases, this might even have some implications for complexity theory. So for example, are very, very low depth noisy circuits equivalent in power to noiseless circuits? And so, and I'm going to be considering a threshold theorem, which at its heart is, it's a map between two circuits. So somebody hands me some circuit M. It's got some depth and width, and I'm going to apply my fault tolerant scheme to convert this to a new circuit, M bar, that I'm going to demand simulates the original circuit in the sense that it produces an output distribution that's close to the original one, subject to some local noise. And I won't really get into what I mean by local, but just know that it's noise at a rate that's not too high. So this P star here you should think of as roughly, say, 1/2 of the threshold value or something like this. And then the thing I want to analyze is the dimensions of this new circuit with respect to the old circuit. So how much deeper is it and how much wider is it? And so I call this the depth overhead or the width overhead. And so there's kind of a long history of fault tolerance and threshold theorems going back all the way to the 90s. And the parameter I'm going to focus on is this parameter that I call the volume. So everything in this talk will be in terms of the volume. And I'm just going to require that the circuit that I'm asked to simulate isn't like pathologically deep or anything like this. And then just as an additional simplification, let's go ahead and restrict this circuit to be Clifford plus some third level gate like T or CCZ. And this kind of just separates out the unitary synthesis overhead from kind of everything else going on with fault tolerance. And then all these constructions have slightly different models of classical computation, and I don't want to get into that. So kind of we start out in the 90s with kind of constructions based on concatenated codes or surface codes where we have polylogarithmic depth and width blow up. So these are kind of the constructions that are practical for our purposes. But then kind of in the mid 2010s, we start to see constructions appearing that have constant space overhead. And I think this is quite cool because once you have constant space overhead, you just have to look at the time. And then oftentimes you can tunably trade off between the width and depth overhead up to a certain point. Sort of you can tune to both extremes, or very nearly so. So up until last year, the state of the art was this paper by Yamasaki and Kawashi using these concatenated quantum Hamming codes, and this achieved quasi-polylogarithmic time in the circuit size. So this is a function that grows faster than the power of logarithm. And so our result kind of improves on this, and we get almost what we think is almost optimal time overhead. So we achieve nearly logarithmic time overhead and constant space overhead. And there's a slightly simpler construction that appeared around the same time that gets slightly worse time overhead, but it's a much simpler proof, and it uses fairly different techniques. So I encourage you to also look at this other paper. And in general, fault-tolerance threshold theorems kind of split into two camps. If they use concatenated codes, like the early works and this newer work by Yamasaki and Kawashi, and or into using sort of quantum low-density parity check codes, which I'll talk a little bit about in a moment. So, for example, this paper by Tamiya, Kawashi, Yamasaki, and our paper. And we actually demand something that's a little bit stronger. In our construction, in order to get the lowest possible time overhead, we actually require a quantum locally testable code. And to our knowledge, this is actually the first time that this has been needed for a fault tolerance application. So let me just briefly state our model of computation and the main result. So I'm going to have a circuit that's on qubits, and the circuit I produce is going to be on qubits. Later, we're going to use some qubits in the middle, but the input and output circuits will be on qubits. And I'm going to demand that it's Clifford plus CCZ. And I'm going to have these noisy quantum operations. So my circuit itself is going to be layers of quantum operations sandwiched between these layers of classical computation. And these layers you can think of as just single layers of gates, and they can be noisy. This auxiliary computation I'm going to assume to be perfect, and then for convenience, I'm going to assume I'm going to allow it to be slightly super constant depth. This isn't really essential. We can remove this, but it just makes the accounting a little bit easier. And it's actually quite important that this is perfect. And then again, we get this nearly logarithmic time overhead. And then if you'd like to see this this Tamiya, Kawashi, Yamasaki paper, this doesn't make this assumption on the classical computation. Great, so now I'm going to talk a little bit about how we achieve this result and sort of our techniques. And you should really think of this as the guide. We're going to start with some code that's going to be the heart of our construction. And then we're going to slowly build up from there and get more and more complicated operations that we are allowed to do. So we're going to walk through, starting with transversal gates, and then we're going to distill some more complicated states, and then some more complicated states, and then we're going to put it all together to get the main result. And so if you ever lost, this will appear in the top right corner, and you can see where we are and what we've gone through. So, okay, so the computational code, which is what I call kind of the code that all our logical information is encoded in, it's going to be a quantum LDPC code, which is defined by a sparse set of X and Z checks. And further, I'm going to require it to be a quantum locally testable code. And all you need to know is that the syndrome weight, so I go and measure this list of checks. The syndrome weight is proportional to the size of the error that's acted on my code state. So this will be used at the very, very end to essentially quickly verify states. And so the QLTC that we use is this construction by Denier, Lin, and Vidic. And it's not quite optimal in the sense that the distance and soundness, ideally we'd like this to be constant, but that's not a problem for us. This enters into our proof as log-log factors, so we're pretty okay there. But we need a decoder for it, so we have to first construct a single-shot decoder for this code family. And for those of you that aren't familiar with single-shot decoders, roughly think of it as we get a single round of syndrome measurement, and we want to process it. And if the input error and the measurement error is not too large, then we have this guarantee that the output error is proportional to the measurement error, sort of that my decoder maybe gets stuck in some places, or maybe it makes some mistakes, but that's fine. So we constructed single-shot decoder for this code family with a decoding radius. So this guarantee that I need is roughly proportional to the distance. And so this is actually an adversarial noise decoder. We can reduce the stochastic noise case to the adversarial noise case, but I won't get into that here. And if you don't want to read about constructions of QLTCs or constructions of single-shot decoders, you can just take this as a given and treat it as a black box. We don't actually need any further properties besides QLTC and the existence of the single-shot decoder. OK, so now let's build up our gate set a little bit more. So because my code is QLDPC, this gives me a very natural and fault-tolerant way to measure the syndrome. So that gives me my logical identity. Kind of in some sense, the spread of errors is very, very well controlled. Because it's a stabilizer code, I get arbitrary logical poly operations. And then because it's a CSS code, I get transversal X and Z basis measurements, and then also transversal C0 for free. This seems like a very limited gate set, but actually this is sufficient to do gate teleportation. So for those of you that haven't seen gate teleportation before, essentially what I'm going to do is assume that first that I have some resource state here, and the rest of the talk I'll mostly be talking about how to prepare these resource states. Then I can consume it in just a teleportation protocol where I have my state that I want to apply the operation to. I do some gates and measurement, and then up to this correction here, I have the state that I'm like to apply. Now, if this U here is Clifford, then this right here, this fix-up operation is itself a poly correction, which we have already. So this gate set alone, just these very simple requirements on the structure of the code, is sufficient for us to do gate teleportation. So now let's just, I'm going to set aside the preparation of these resource states. We'll get back to that. If I have this, what's the high-level strategy? Well, so let's start with the circuit that somebody gives to me. And it has layers of gates. So all these gates you should imagine as happening in parallel in one step of the circuit. And what I'm going to do is, at every time step, I'm going to prepare and consume a bunch of resource states. So I have to schedule that. And so first, I'm going to break up this circuit. I'm going to assign the qubits of the circuit arbitrarily to these registers. And these registers will be encoded in these very small code blocks of roughly logarithmic size. But now there's a problem. I only know how to do gate teleportation for single gates at a time, right? So I have to kind of, I have to schedule my gates. So I'm going to write down this graph where every edge corresponds to a gate in a particular time step, and every vertex corresponds to each of these registers. And then what I'm going to do is compute an edge coloring of this graph. It looks something like this. And I only need logarithmic log v number of colors to edge color this, and I can do this approximately efficiently, so there's no issues with that. And this is actually the main time overhead. So in our construction, this is where this log is coming from. And then for some reasons that I won't really get into, we have to do some further serialization, and that's our little low of 1. So this is the main bottleneck in our construction. And everywhere here, I'm suppressing log-log factors whenever they're subleading. I will say this. OK, so now I need to tell you how to prepare these resource states. And resource state distillation protocols, you should think of it as I'm given some number of noisy resource states, and I want to convert them into less noisy resource states. So you should think of this as some protocol that I'm doing on the logical level, in this case with my transversal gates. And I need to be able to do this in very low time overhead. So I'm actually going to prepare a lot of noisy, I'm going to take in a lot of noisy copies and then output a lot of less noisy copies. And as it turns out, whenever I have a code supporting certain transversal gates, this automatically gives me a state distillation protocol with a small amount of extra work. And In particular, for this protocol, you should think of it as error correcting instead of error detecting, which is a slight difference from the usual distillation process where you just throw everything in the trash if you detect an error. And repeated distillation you can think of as somewhat analogous to a concatenated code scheme. And in fact, we have concatenated error correcting code schemes that achieve constant rate. We saw this in the Yamasaki-Kawashi paper. We can just take this thing and then use it to distill the stabilizer states that we're going to use for Clifford, for our Clifford circuits, or sorry, our teleported Clifford gates. So now, and then once we do that, because it's concatenated, this actually gives us some slight improvements to, or actually some quite strong improvements to the depth overhead required, because we need a low space-time overhead instead of simply a good ratio of input to output states. So here our depth is polylog-log. And the ratio of input to output states is constant. So okay, now what about our magic states? So we have to do the same thing, but it's going to be a little bit more tricky. So here, the thing that I really care about is, again, the space-time cost. And you saw yesterday that it's common to analyze the output of a magic state distillation scheme in terms of the ratio of input to output states. We're going to do something different. We're actually going to look at the gate count per output magic states. And here, we don't know how to get constant ratio. But in our case, we do know how to get something that is kind of still sub-logarithmic in the output error rate. So if you have a magic state distillation scheme with this distillation, or this power gamma constant, then that's automatically an upper bound on this other constant gamma tilde, which I'm defining in this way. So what we prove is that there exists a simple construction of magic state distillation with this ratio of gate count to output magic states being sub-logarithmic. And it relies on these punctured quantum Reed-Solomon codes over qubits that are a power of 2 dimension. And so our first result is that that we can have a punctured quantum Reed-Solomon code with this transversal CCZ gate with good parameters over this larger alphabet. And so our strategy is going to, we need something with qubits, and so our strategy is going to be to simulate the qubits, or the qubits with the qubits. And for some technical reasons, we'll grow the field size as we step along later and apply rounds of the distillation protocol. So we're going to be distilling this funny-looking state, which is just the QDIT CCZ gate. And we can simulate this QDIT CCZ with qubits, and then we'll just convert it back using Clifford operations, so no big deal. And then this multiple round issue, so if you try to take some of the magic state distillation protocols you saw yesterday, you may in general have to do a very deep syndromic, or very deep unencoding circuit. So you end up with your magic states that are encoded. They're very, they have maybe low error, but then you pay a very large space-time cost in order to get them out. So you have to be a little bit more careful than just examining the ratio. And so what we get is a magic state distillation scheme with, again, this very low depth, but now we pay a little bit. So this is our little of 1, in that we don't quite get as many output magic states as we would like. So finally, I have to tell you how I'm going to produce the noisy inputs for this distillation process. Kind of the heart of the construction is running this distillation, but getting the inputs actually turns out to be quite challenging. So suppose I have a circuit that prepares for me a logical state of my computational code, and it doesn't have to be fault tolerant or anything like that. And the trick that I'm going to do is I'm going to simulate this thing using some concatenated codes, such that it fails with some constant probability. Think like 1/100. And I couldn't use concatenated codes for error or for computation because kind of the error suppression there's an overhead here, but for preparing these initial noisy states, that's fine because I'm allowing them to fail. And when I do that, this has some small costs associated with it, but it's fine because it's sub-logarithmic. But now there's a problem. The error correction gadget that we have, recall at the very beginning, my single-shot decoder, in order to have any guarantees at all on the output, requires that my input error is not too big. And in general, this circuit P, whenever it fails, it could do something horrible. And so I like to call these logical leakage errors because it has a lot of similarities with with physical level leakage. Kind of these leaked code blocks kind of can poison the rest of your computation. So you can't do any further processing with it, and you have to verify that they're not leaked before letting it into the computation to do, for example, distillation. So what happens if I'm very far from the code space? So here I'm kind of plotting a cartoon where I have some error and its syndrome. And if my code's LDPC, then I have an upper bound. I know that if I have a small error, my syndrome can't be too big. But for generic QLDPC code, I can actually be very far from the code space and have very small syndrome. So it's actually quite difficult to verify that my state isn't too damaged. Fortunately, the QLTC property really allows us to do this verification because in a QLTC, the syndrome lives in this cone. Sort of, if I'm very far from the code space, then I know that I have a very high syndrome. And so even if I have some measurement errors, that's going to be OK because I can just arrange such that that my bound on the measurement errors, I can arrange for a threshold such that if I have a false negative or false positive, that the state still is not too damaged with high probability. So I'm just going to measure that I'm going to get my output state, which I believe is probably OK. And then I'm just going to measure the syndrome. And if it's not too bad, I'm just going to accept it and otherwise reject. And that's going to range such that my states are not too damaged. So finally, I have to tell you how to put this all together. And this is where we really had to make some innovations in terms of analysis techniques for fault tolerance threshold theorems. And roughly, I'll just go through this very quickly. If I have some gadget, which is subject to some errors, I want some statement along the lines of that if I have a good input and my set of errors is not bad in a certain sense, that I have a good output. And so what I'm going to do is I'm going to write down these sets that if my fault, the set of noisy locations, doesn't contain any one of these sets, then I know that the output is good in a certain sense. And as it turns out, it's very convenient to associate this family of sets to polynomials. Because this common local stochastic noise model, I can bound the probability if the set of faulty locations is distributed in this local stochastic noise model, then I can bound the probability that my fault is bad by the evaluation of this polynomial, which we call the weight enumerator, at the noise parameter of my channel, kind of just simple union bound. You might say, OK, well, that's trivial. But it turns out, actually, that in order to analyze our gadgets, so our gadgets we're taking simple gadgets and then composing them and building up more and more complicated gadgets. So our distillation, this is the first threshold theorem, to my knowledge, to use distillation. It's quite involved to analyze, right? We're going to have a lot of places that could fail, but that's going to be OK. So there's actual operational meaning to multiplying the polynomials, adding them, and composing them. And we use all three operations in our threshold proof. So just to give an idea, kind of this is the actual sketch of the proof, and there's just a lot of moving parts. So we had to use a QLTC in a highly non-trivial way to do the state preparation scheme. We gave a low space-time overhead, a magic state distillation scheme, and then we introduced this tool to analyze fault-tolerant gadgets and build more complicated gadgets out of simpler ones. And then this is also, to my knowledge, the first fault tolerance theorem that actually uses distillation. And there's our main result. Thank you.
Hello, thanks for the great talk. I have two quick questions. The first is, you use stochastic noise model, but do you think that your result should generalize also to, like, that you can implement each gate with diamond norm error? Like, yeah, the second question, I'm curious about what do you mean that folklore surface code? Do you mean that there is no proof that you can sample from TV distance epsilon close to the noiseless circuit?
Right, so about the first one, yeah, indeed, our techniques very straightforwardly generalize. You can essentially use the same techniques of Aharonov and Ben-Or to prove threshold theorems in other noise models. So that's very straightforward. Now, as for the second question, to my knowledge, nobody has written down a formal threshold proof in the spirit of, you give me a circuit, I give you a new circuit that samples the output to some TBD, or sorry, the output distribution to some TBD. This is something that, for some reason, has just never been written down. And it does involve analyzing things like logical level magic state distillation, stuff like that, and that's a very involved end-to-end proof.
Thanks for the nice talk. Maybe I missed this, but do you have to worry about the speed of your classical processing now? Because if you're having like a polylog time overhead, you need to make sure you, like linear time classical processing sounds like a problem.
Right, so the classical processing, so the depth it's a polylog-log depth parallel classical circuit, and we can actually remove this without too much trouble. It's just some more counting.
Okay, great.
However, there is kind of an unavoidable, you have to do a parity at one point, which is log size. Oop.
You mentioned being able to trade off space and time. If you care only about time complexity and space is like free, what does this algorithm turn into?
So we can get all the way down to log depth. No, sorry. In our model, you can get all the way down to constant time overhead. Whenever you're looking at time like this, I think it's really important to be very careful about the model of computation because then you probably care about not only classical processing, but kind of yeah, you probably care about that depth. And there's this parity that you have to compute, and that's going to cause some polylog-log time overhead blowup. So up to a point, I can trade them off, but unfortunately, you can't push it all the way.
So if you go down to polylog-log time or something, do you get exponential space overhead?
No, you get log 1 plus little o1 space overhead.
Sounds pretty good.
There's no more questions. Let's thank Chris again.